We've seen that the right-hand side of a non-homogeneous differential equation often ends up being e to the at times something else. So far, Laplace transform tables don't say how to take care of products. It's not as easy as saying the Laplace transform of a product equals the product of Laplace transforms. But actually, it's almost as easy as that. So the first shifting theorem tells us that if the Laplace transform of f of t equals capital F of s, then the Laplace transform of e to the at f of t equals f of s minus a. So multiplying by e to the at here just means replacing the s with s minus a there. Conversely, if we're taking inverse Laplace transforms, and if we know that the inverse Laplace transform of capital F of s is little f of t, then the Laplace transform of capital F of s minus a equals e to the at f of t. So if we ever see s minus a constant where we wish there were just an s, it's actually not too hard to perform the inverse Laplace transform. We're just going to multiply by e to the at and pretend that we're just an s. So this is not too hard to prove. Let's suppose that Laplace transform of f of t equals capital F of s. Then if we want to take the Laplace transform of e to the at f of t, by definition that's the integral from 0 to infinity of e to the negative st times this, so e to the at f of t dt. And that's the integral of, we can combine the exponentials and write this as e to the negative s plus a t f of t dt. And I'm going to pull the negative out so it looks a little bit like the definition of Laplace transform. So that's the integral from 0 to infinity of e to the negative s minus a t f of t dt. Alright, so the Laplace transform of e to the at f of t is this integral. Now let's look at what f of s minus a should be. And then show that the two expressions are equal. So f of s is defined to be the integral from 0 to infinity e to the negative st f of t dt. So if we plug in s minus a for s, we get the integral from 0 to infinity of e to the negative s minus a t f of t dt. But that's exactly what we got here by taking Laplace transform of e to the at f of t. So I guess f of s minus a and the Laplace transform of e to the at f of t are the same, which is what the first shifting theorem is saying. Alright, so let's do some examples. First we'll do examples of the Laplace transform direction, then we can do examples of the inverse Laplace transforming direction. Alright, what if we wanted to take the Laplace transform of t to the k e to the at? Well, the Laplace transform of just t to the k is k factorial over s to the k plus 1. So we copy this number into the numerator with the factorial, and then we add 1 and put that as a power of s in the denominator. So that means that if we put the e to the at back in there, then it's just k factorial over, we replace the s with s minus a. So k factorial over s minus a to the k plus 1. Another example, what if we have Laplace transform of e to the at times sine of bt? Well, if we just had Laplace transform of sine of bt, then that would be equal to b of s squared plus b squared, b over s squared plus b squared. So that means if we take the Laplace transform of e to the at times sine of bt, we write the same thing but replace every s with an s minus a. So we have b over s minus a squared plus b squared. And what if we wanted Laplace transform of e to the at cosine bt? Well, Laplace transform of cosine of bt without the exponential is s over s squared plus b squared. So that means that this Laplace transform is, we'll just plug in an s minus a everywhere there was an s minus a over s minus a squared plus b squared. Alright, now let's do some examples of the inverse direction. So let me write the inverse direction here. If the inverse Laplace transform of f of s equals f of t, then the Laplace transform of f of s minus a equals e to the at f of t. So for example, what if we wanted to take the inverse Laplace transform of 18 over s minus 2 to the fourth? So this looks a little bit like something over s to the fourth, and if it were something, if that something were a 3 factorial, then the inverse Laplace transform of 3 factorial over s to the fourth would be t cubed. So it's not exactly that, because the s, where we expect to see an s, we see s minus 2 instead. So I'm going to rewrite this 18 over s minus 2 to the fourth with I want to keep 6 on the inside to be my 3 factorial, so I guess I'll move 3 to the outside. Then I'll pretend this is just 6 over s to the 4th, and that'll give me t cubed. And then since it's s minus 2, I multiply by e to the 2t before my t cubed. Alright, another example. What if we have L inverse of s minus 1 over s minus 1 squared plus 16? So this looks a little bit like s over s squared plus 16. And we know that L inverse of s over s squared plus 16 is cosine of 4t. Now since we see s minus 1 everywhere, we expected to see an s. And we write down cosine 4t, and we just have to multiply by e to the t. Alright, now in the inverse direction things can get a little trickier than these two examples, so let me put a tricky example up. So it's trickier if the s minus a part isn't shown explicitly. So for example, what if we had the inverse Laplace transform of s minus 3 over s squared plus 4s plus 10. So we see an s minus 3 here, but we don't see s minus 3's there. So we have to somehow play with this so that all the s's involved are s minus something, but they all have to be that. So one thing we can sort of see in here is that we have s squared plus 4s, so it sort of looks like the beginning s squared plus 4s plus 4, which is s plus 2 squared. So we can make it that, and then we can change this s minus 3 into s plus 2 minus 5. So if we see in the denominator we wish we had s plus 2 squared, something like that, because we see a little bit of s plus 2 squared, we can rewrite this as s plus, say, s squared plus 4s plus 4 plus 6. And then this is s plus 2 squared. And then in the numerator we could have s plus 2 minus 5, because 2 minus 5 is minus 3. So s plus 2 minus 5 over s plus 2 squared plus 6. Alright, so it's a little bit closer. Now this looks a little like s over s squared plus a squared and a over s squared plus a squared, which we could do separately. It's not exactly that. So let's play with this again. And let's write this as s plus 2 over s plus 2 squared plus 6 plus, now if we had a constant over s squared plus a squared, we'd hope that that constant would be a. So in this case it's, I wish we had square root of 6 over s plus 2 squared plus 6. Well, we don't have square root of 6, we have negative 5. But we can factor out a square root of 6, and then here, I guess we can write negative 5 over square root of 6 as the coefficient, because the square root of 6 is canceled and that equals negative 5. So we haven't done anything other than factor out a constant so that we get the top part of the fraction that we wish we had. Now the inverse Laplace transform of s plus 2 over s plus 2 squared plus 6 equals e to the negative 2t, because this is s minus negative 2, cosine of square root of this number. So square root of 6 times t. And then this part is sine. So this part is negative 5 over square root of 6 sine of square root of 6t times e to the negative 2t. E to the negative 2t, because s plus 2 is the same as s minus negative 2. So it turns out that L inverse of this fraction is e to the negative 2t cosine square root of 6t plus e to the negative 2t negative 5 over square root of 6 sine of square root of 6t. Alright, now let's do an example of a differential equation which is going to require the shifting theorem when we solve it by the Laplace transform method. Alright, let's solve y prime minus y equals 8 e to the t with initial conditions y of 0 and y prime of 0 are both equal to 0. And let's say using Laplace transform. Alright, so we'll take Laplace transform on both sides. So L of y double prime minus capital Y equals L of 8 e to the t. So that means that s squared y minus s f of 0 minus f prime of 0 equals 8 1 over s minus 1, because this is e to the 1t. Now f of 0 and f prime of 0 are both 0, so that goes away. Oops, I forgot the minus y here. Minus y. This is just the L of y double prime part. Alright, so this goes away and that goes away, and we're left with y times s squared minus 1 equals 8 over s minus 1. So dividing by s squared minus 1, we have y equals 8 over s minus 1 times s squared minus 1. S squared minus 1 is s plus 1, s minus 1. So we're going to have two s minus 1s here. S minus 1 squared, s plus 1. Alright, now, so we've solved for y, but we need to use partial fractions to take the inverse Laplace transform of y. So using partial fractions, we'll write 8 over s minus 1 squared s plus 1 as a over s plus 1 plus b over s minus 1 plus c over s minus 1 squared. Because when you have a factor to a power, you have to consider all of the exponents from 1 up to that power. So we need s minus 1 to the first and s minus 1 to the second. Now let's multiply by s minus 1 squared s plus 1 to clear denominators. So we have 8 equals a. S plus 1 is going to cancel the s plus 1, and we'll have s minus 1 squared plus b. One of the s minus 1s is going to cancel that s minus 1, and we'll still have another s minus 1 and the s plus 1. And then c, s minus 1 squared is going to cancel that, and we have s plus 1. Alright, there's two obvious numbers we can plug in to make parts of the expression on the right go away. That's s equals 1 and s equals negative 1. So if we plug in s equals 1, then we get 8. This disappears. That disappears. 8 equals c times 2. Alright, that was easy. So now we have c equals 4. And what if we try s equals negative 1? 8 equals a times negative 1 minus 1, negative 2 squared. Negative 2 squared is 4. 4a. That disappears. And that disappears. Okay, that was pretty easy. So I guess a equals 2. Now let's rewrite this with the a and c solved for and see what we can do about b. So 8 equals a is 2. 2 times s minus 1 squared plus b we don't know. S minus 1 times s plus 1 plus c we know is 4. 4 c plus 4 times s plus 1. Alright, we could compare the constant terms on both sides of the equation, or the coefficients of s, or the coefficients of s squared. Or we could try plugging in another number for s and see if we're lucky. If we plug in another number for s, we're just going to have an equation in one variable, b, which we can probably solve. So let's try s equals 0 and see if that's something we can solve. So 8 equals 2 times negative 1 squared, which is 1, plus b times negative 1 times 1, so it's negative 1, plus 4 times 0 plus 1, which is 1. So that means that 8 equals 2 minus b plus 4, which means that if we subtract 6 from both sides, 2 equals minus b, which means that b equals negative 2. Alright, so now that we've solved for a, b, and c, y is this expression. So y is a over s plus 1, 2 times 1 over s plus 1. B is negative 2, minus 2 times 1 over s minus 1. C is 4, plus 4, 1 over s minus 1 squared. So the inverse Laplace transform of y equals 2 inverse Laplace transform of 1 over s plus 1 minus 2 times inverse Laplace transform of 1 over s minus 1 plus 4 inverse Laplace transform of 1 over s minus 1 squared. Alright, two of these things that we want to take inverse Laplace transforms of look a little bit like 1 over s. And one looks like 1 over s squared. So let's recall for ourselves what would happen if we were to take inverse Laplace transforms of those two functions. So this is hopefully factorial over s to 1 greater power than the factorial is. Down here we have s to the 0 plus 1, and 0 factorial is 1. So this is exactly the form we want. 0 factorial over s to the 0 plus 1. So the inverse Laplace transform is t to the 0, which is 1. Alright, what about the one with the squared? Inverse Laplace transform of 1 over s squared equals inverse Laplace transform of, this is s to the 1 plus 1, and 1 as well as being 0 factorial is also 1 factorial. So this is exactly the form we want too. So that equals t to the first, which is t. Okay, so now we've got these two formulas ready. We can tackle all three of the terms that we need to take inverse Laplace transforms of. So that means that the inverse Laplace transform of y equals 2 times, now this would just be 1, but since we have s plus 1 where we expected to see an s, we multiply e, I'll multiply by e to the negative t before writing 1. And again, s plus 1 equals s minus negative 1. So that's why we got negative t here. So minus 2, 1 over s basically, except we see an s minus 1 where we expected to see an s. Because of the s minus 1, we multiply by e to the 1t, e to the t, before we write 1. And here we have basically 1 over s squared, except we see s minus 1 where we expected to see an s. So just like here, we write e to the t, e to the 1t, because this is s minus 1, and then t. So we have 2e to the negative t minus 2e to the t plus 4t e to the t. And I guess we could check that this actually satisfies the differential equation. let's check our solution. So y equals 2e to the negative t minus 2e to the t plus 4t e to the t. We need the second derivative, so first derivative first. First derivative is negative 2e to the negative t minus 2e to the t plus 4. Let's say derivative of the first times the second is 1e to the t, plus derivative of the second times the first is t e to the t. So 1 plus t e to the t. Now we've got a 4e to the t, which we can combine with a negative 2e to the t. Negative 2e to the negative t minus 2e to the t plus 4e to the t is plus 2e to the t plus 4t e to the t. Y double prime is positive 2e to the negative t plus 2e to the t plus 4. Again, the derivative of t e to the t is derivative of the first times the second plus derivative of the second times the first, which will give us a 1 plus t e to the t. And now we've got 2e to the t and 4e to the t, which we combine to make 6e to the t plus 4t e to the t. Alright, so how are these supposed to relate? If we take second derivative minus y, we're supposed to get 8e to the t. So y double prime minus y equals this minus 2e to the negative t minus 2e to the t plus 4t e to the t. 2e to the negative t minus 2e to the negative t is 0. 6e to the t minus negative 2e to the t is 8e to the t. And then 4t e to the t minus 4t e to the t is 0t e to the t. So we got 8e to the t, which is what we're supposed to get. And supposedly, if we plug in 0 to y and the derivative, we get 0. So maybe we'll just check that. Y of 0 is 2 times 1 minus 2 times 1 plus 4 times 0 times 1, that's 0. So we've got 2 minus 2, which is 0. Y prime of 0 is minus 2 times 1 plus 2 times 1 plus 4 times 0 times 1. So again, minus 2 plus 2, which is 0. Okay, so we did actually find a solution of this differential equation. In fact, a solution of the initial value problem, which is the solution of the differential equation that satisfies those two initial conditions too. The end.